Okay, it's July 13th. We finally reached the day where we get to go to UCSD, and we're using the ViewSizer 3000, which is an awesome testing machine that allows us to view how many nanoparticles, the size and the distribution of nanoparticles within any sample. So in the way that we're setting up our sample collection, we're trying to duplicate kind of real-world interactions and the way we would actually drink water, the way we interact with those containers and everything else. So there is a downside to doing that. That really is not pure lab controls like we would introduce if we really wanted to determine the question of, are there any nanoparticles in these samples? But that's not the question we're trying to ask. What we're really trying to do is rank order our samples to say which of these has the least amount of nanoparticles, including likely nanoplastics within that sample. We're using real-world containers to collect them. This is what I drink out of every day, the Bamba bottle. These are going to be brand new. We've got a protocol where we're going to be washing these with a liquid detergent that is fragrance-free and one of the free and clear type detergents. We're going to rinse many times, and then we're going to rinse with our samples several times as well. And then we finally collect the samples after that final rinse to take into UCSD. These are stainless steel containers with stainless steel caps as well. There is a silicone ring that's a gasket, but it has very little contact with the actual sample itself because the gasket's around there. The rest of the material is all stainless steel. So we're planning on taking 4 samples today. First one is just going to be a straight tap water. And we have our tap water arranged in 2 different types. On the cold side of our tap water, it is not going through the water softener. On the hot side of our tap water, it is going through the water softener. So just because we're curious, we're going to take 2 samples from the tap water, 1 cold and 1 hot, to see if they're any different in the level of nanoplastics within them. We're also going to take a reverse osmosis sample, and that reverse osmosis is what I drink most of the time. And we're about harm reduction with the plastic, but in reverse osmosis may be the best way to reduce nanoplastics and microplastics in your water. But as you can see, it goes through a lot of plastic components and a lot of plastic tubing, as well as the filter itself. The RO filter is made of plastic. So when you're forcing water through all that plastic, it's possible that it could be adding plastic rather than reducing plastic. And that's one of the things we hope to find out today as well. And then the last sample we're going to do is through the refrigerator, normal refrigerator filtered water, and just see what that's like. We're also going to be testing a few more samples today, just purchased water. We're going to purchase bottles of US glass bottled water, plastic bottled water, and then 1 international base, maybe like an Italian spring water as well to test.
What we're doing is we are loading up pre-purified water into our NTA, and we are exposing it to 3 different colored lasers. Ideally, what we would see is only a couple of nanoparticles actually popping up on screen as little tiny dots that kind of just meander across the window.
So right now we're starting an acquisition with 100% isopropanol alcohol, which should be pretty relatively particle free. So right now we're seeing on the screen that there's little to no particles being trapped for the current measurement that is happening right now. And so right now it's taking about 20 to 30 second videos where it'll go ahead and measure the particle diffusion over time. And from that diffusion speed, it's going to calculate the particle size distribution, which is correlated for diffusion based on particle size. Something that is small is going to move much faster than something that is big in suspension. And so right now it is currently seeing less than 10 particles on the screen, which means that this is very particle free, much more than what you would expect with the 20 nanometer filtered HPLC grade water.
This was 18 mega ohm water that we tested on our system, and even though we saw a lot of particles visually on the camera, what was counted, we got an actual concentration of about 200,000 particles per milliliter, which is a extremely low amount of particles relatively for our application. So, and all of these particles are actually smaller than 20 nanometers on their own, anyways. And because of that, this is water I would actually trust in most scientific applications without any worries about other contaminants getting in my source. Um, Typically in like deionized water, so like deionized water you would find at like the store. This would actually say something like 2 times 10 to the eighth. So you'd have like 100 million, or actually don't. I'm bad at doing math in my head, but you'd have several million particles per mil. But that would still be like water that you would consider safe to drink on that scale, but might mess with someone doing like nanoparticle research, which this water would be good enough for.
So what we end up seeing with the testing today through nanoparticle tracking analysis is that reverse osmosis showed the smallest particulate contamination, what we suspect. Um, Next from that, we also have Mountain Valley spring water having the next few amount of particulate contamination, along with refrigeration produced water. Kirkland water and San Pellegrino water both had a bit more what we suspect mineral particulates inside, and so those showed us wider distributions within the data sets. If we look at the data by volume, we end up seeing that a bigger percentage of the larger particulates inside of the Kirkland bottle as well as the San Pellegrino water um, are much more out of the range of what we expect for sort of particulate free water, which would be sub 20 nanometer particulates. Reverse osmosis in this view also closer matches to the Mountain Valley and refrigerated water. In this case, there's much smaller abundance of particulates and much smaller particle count by an order of magnitude for most samples. So right now these sample cups were prepared, and right now we're going to do X-ray fluorescence spectroscopy. So the samples are going to have X-rays shined on them, and there's going to be an induced fluorescence that will be discrete based on the elements that are present. And so this is for elemental identification from sodium down to americium in the periodic table. And so with this technique, we're going to confirm whether the particulates that we saw with NTA are they going to be silica-based or mineral-based. So right now we're going to do some UV-vis absorbance testing on the samples. The reason you might want to do UV-vis testing in this case is that plastics absorb in the UV. And so right now it's currently loaded inside of a quartz cuvette, which is not going to be UV active. And so in this case, any absorbance we see in that UV region is going to be due to any plastic that is going to be inside of the sample. And so this is going to be complementary to the XRF testing that we're currently doing to confirm if there's mineral particulates inside. So this testing is going to be right now to confirm that there's that plastic particulate contamination within the water samples. So across the UV-vis testing that was done on the refrigerated sample, the Mountain Valley water, Kirkland-based water, and the reverse osmosis, There was no spectral difference across the UV range to confirm that there was any plastic contamination in the samples. Yeah, so through Raman spectroscopy, unfortunately, we did not confirm the presence of any particulates within the samples tested, which were reverse osmosis as well as Kirkland. All that was visible was just background due to the glass substrate used to place the sample on, as well as the stage of the Raman spectrometer.
So it's the Thursday after our Monday testing session at UCSD. And well, I would say the summary is that our results were totally inconclusive, but we had lots of positive experiences during the day as far as learnings about what we really need to test in the future and evolutions of how we need to do this, some relationship building within the laboratory. And we really had fantastic learning experiences using 4 different really sophisticated pieces of equipment to do both really particle sizing and distribution, and then really the chemical and elemental determination. And that was really cool to be able to do that. So I think some outcomes are I'm going to be reducing the focus of what we're testing in the future because it's going to get more complicated. So I'm really going to be focusing mostly around what I'd like to be drinking, especially after the testing we did, which is reverse osmosis water. And in addition to that, I think the testing might include some of the bottled waters, the glass bottled waters, because I've got an inner knowing that I can trust those, but I'd like to validate that with some testing in the future as well. But the bottled waters will be more complicated to test. A big learning was, there's really so little particulate matter within any of the samples compared to the dissolved solids that move freely as ions between the water molecules. Because the mass of those dissolved solids is so much greater than the actual particles that are left over that we want to test, it's really difficult to get a separate read between those. I think that's the work going forward of how we do that. Ultimately, the debrief is inconclusive so far, some great learning experiences, and now we need to regroup, go back to the drawing board for the next round of testing.